Good afternoon, everyone, and welcome to today's Geo lecture. Today I'm joined by Katie Szkornik. I hope I pronounced that right, even after our little run practice this, just a moment ago. Today we're going to be looking at coastal environments and understanding the impact of sea level rise and climate change on these spaces. Katie is a senior lecturer at the University of Kiel, and she studies coastal regions and reconstructing the Holocene sea level change from salt marsh sediments. If you do have any questions throughout the lecture, please leave them in the live chat on the side, and Katie will answer those at the end. Apologies for the doorbell going. These things happen when we're all working from home, etc. So I'm going to hand over to Katie now, and I hope you enjoy.
Brilliant. Thanks very much, Harriet, and hello, everyone. So my name is Katie Szkornik, and I'm a senior lecturer in physical geography at Kiel University in the UK. For those of you that don't know where Kiel is, we're located between Birmingham and Manchester, and we have a beautiful rural campus with lots of geography around us. So today I'm going to be talking to you about coastal environments, and in particular thinking about the impacts of sea level rise and climate change on coastal environments, both presently and also in the future. It's a really topical area, and it's a really important area of research within physical geography and other disciplines. So if we start off by thinking about the vulnerability of different coastlines around the world, depending on which textbook you read, but there's estimated to be around about 500,000 kilometres of coastline around the world, and approximately 50% of the world's population live within 2 kilometres of coastline. And if we think about some countries around the world, like Australia, for example, we have a real dominance of coastal cities. So in Australia, around about 80% of the population live in a coastal city, so both down the eastern seaboard and also Perth on the western seaboard. So the coastline is a really popular place for populations. It's a major source of residential populations, but also it's a place where industry often locates as well, sometimes because the land is cheaper, but sometimes because the industry requires access, for example, to water supplies. And so we have a vast proportion of the world's population living very close to the coastline. Coastal environments are very dynamic environments. They're changing over lots of different timescales. So any coastline is changing on a minute-by-minute basis due to the action of the waves, changing on an hourly basis due to the action of tides, and it's changing on slightly longer-term basis due to the action of, for example, rising relative sea levels. So coastal environments are dynamic environments. They're rapidly changing, and they're really vulnerable to future climate change and in particular sea level rise. So I want to start by thinking about some of the vulnerability in different coastal environments. So much of this talk is focusing on sea level rise, but actually climate change threatens coasts more broadly for a number of associated hazards. So there's a number of images on this slide in front of us. In the top left, we've got an image of the Japanese tsunami in 2011. On the right, top right, you've got an example of coastal erosion. This is the North Carolina coastline in the United States. We've got lots of low-lying tropical islands, particularly in the Pacific, that are under threat from rising sea levels, but also things like saline intrusion. And then down in the bottom right, you've got an example of a railway line. In this case, this is Devon in the UK, that's threatened by rising sea levels. So when we think about the vulnerability of coastal environments, we're often thinking about the effects of climate change and sea level rise, but actually there's a broader range of coastal hazards that will be affected by changing climate that will impact on these vulnerable environments. So in many locations around the world, some of these other implications will affect that particular coastal area before the rising sea level itself causes the actual flooding of an area. So saline intrusion is a big problem in many coastal environments around the world. And this is where sea levels are rising, but they're not rising enough to yet cause flooding in that particular area, but the saline water is contaminating freshwater underground aquifers. So in these locations of the world where drinking water and water for agricultural purposes is taken from underground aquifers, then the fact that those aquifers are becoming saline because of rising sea levels is a huge problem. It means your drinking water supplies are under threat, and equally important, you don't have a water supply to be able to maintain your agriculture. And that's a real problem in many of the low-lying tropical islands that we have around the world today. So when we think about the vulnerability of coastal environments to sea level rise, it's not just the rising water level itself that's a problem, but it's actually all these associated hazards. So if you change the level of the sea, you affect, for example, coastal erosion, you affect the magnitude and the frequency of flooding, and you have knock-on implications for a number of different processes. So in this diagram here, this diagram is showing you coastal megacities. So megacities are generally cities with a population in excess of 10 million. And if you look at this map, you can see there's a number of coastal megacities that are located in different parts of the world, and they're exposed to a number of different coastal hazards. So if you look at the key down here in the bottom left, anything that comes within sort of these blue lines are threatened by big storm systems, hurricanes, typhoons, cyclones. Where you can see the little green stars, these are low-lying coastal areas, so really at risk from rising sea levels. We've got some coastal megacities that are sitting on river deltas, and then we've got other parts that are threatened by tsunami events as well, particularly those which are close, of course, to plate boundaries. So if you look at the distribution of population around the world, you'll find there's actually a significant amount of the world's population is A, located in coastal environments, but B, located in coastal megacities. And these cities are vulnerable to a number of different coastal hazards. So, for example, particularly if we look at this area around Eastern and Southeast Asia, so we've got the cities of Shanghai, Guangzhou in China, susceptible to a number of different coastal hazards, Tokyo, Manila in the Philippines, Dhaka in Bangladesh. All of these cities contain really big populations, and they are vulnerable to multiple coastal hazards. So understanding coastal environments, understanding processes, understanding how sea level rise is going to affect these environments in the future is really important for being able to mitigate and protect against some of the coastal hazards that these populations face. So I'm just going to talk through some examples now of different coastal hazards that have affected different places around the world in the last 12 months or so. And really this is just to put in perspective some of the different challenges that different locations around the world are facing. So Venice is located in northeastern Italy on the coast of the Adriatic. And Venice has a long history of flooding. In 2019, it experienced the largest floods in about 50 years. So some of you will know that Venice is located on a low-lying coastal plain, and the city is actually built on a series of islands within a lagoon. So it's fairly vulnerable to different coastal processes anyway. In addition to that, there is a unique combination of astronomical, geophysical and meteorological conditions affecting Venice that results in what's known as the aqua alta, so the exceptionally high tides that affect Venice several times a year. So on the one hand, the shape of the Adriatic Sea, so Venice sits at the sort of top end of this narrow funnel known as the Adriatic Sea, and the shape of that particular basin means that the incoming tidal wave, so when the tide comes in, the water is funneled into this basin, focusing on the city of Venice. In addition to this, we have a wind system, so again links to sort of atmospheric systems here. The Sirocco wind is a wind that blows on the Adriatic from the south to the north, and that has the additional effect of funneling water up towards the northern coast of Italy, and particularly in Venice. And finally, in 2009, and as is the case of some of the other floods in Venice, we saw a particularly intense storm event in the foothills of the Dolomites, which are just to the northeast of Venice. This resulted in high rainfall making its way through the river systems and into the Venice Lagoon. So this combination of factors in 2019 resulted in the worst flooding in about 50 years in the city of Venice. A final problem that Venice faces is that the city is actually subsiding. So the land on which the islands on which the city is built, and in fact the whole of the Venice Lagoon, is subsiding. This is mainly due to the abstraction of groundwater from underground aquifers. So this kind of, in some respects, quite a unique but fairly toxic combination of different settings and processes makes Venice really vulnerable to different coastal hazards. If we superimpose on top of this rising relative sea levels, then you can see quite quickly that Venice is one of these very vulnerable cities around the world. Now, in Venice, as part of their plans to try to mitigate against rising sea levels and flooding, they have recently opened the Moses flood barrier system. So this is a series of barriers that have been built across the lagoon entrances into the city of Venice. And when exceptionally high tides are predicted to take place, these barriers rise up out of the water and prevent water coming into the lagoon and flooding the city of Venice. So the Moses flood barrier scheme actually opened in the autumn of 2020. So it is hoped that the flooding problems that Venice has experienced for quite a long time now will hopefully be reduced going forward. And those flood barriers were built to withstand a certain amount of sea level rise that's been incorporated into that modelling as well. So time will tell if the barrier is effective in helping to protect the city of Venice. So after this talk today, I've put a little link here. This is to a CNN news report. It's about a 5-minute video, just gives you an idea of the 2009 flooding in Venice, which I'd encourage you to have a look at after this talk. So a contrasting example, I'll take you to the other side of the world and think about Southeast Asia. So in 2019, Southeast Asia, particularly southeastern China, the area around Shanghai, Taiwan as well, were hit by what's known as a super typhoon, so Typhoon Lekima. So this was a really large typhoon, really intense precipitation event. And again, it's a unique combination of factors that made the area around the city of Shanghai particularly vulnerable to these kind of events. So Shanghai has a population of about 24 million. So it's a huge urban area, a very sprawling urban area that extends across much of the coastal plain. Again, like the situation in Venice, the area is subsiding, so it's sinking because of the abstraction of groundwater. So groundwater is being taken out of the underground aquifers, and as a result, the whole city and surrounding areas is actually sinking slowly, subsiding, and obviously losing elevation. On top of this, we have rising sea levels threatening the area. And finally, the city of Shanghai sits in the direct path of major typhoon events. So typhoons typically associated with high rainfall, flooding, temporary rises in sea level because of the low pressure systems, and tends to cause all kinds of knock-on implications for other natural hazards. So things like landslides, mudslides typically happen in association with these storm events. So again, this unique combination of factors impacting the area of Shanghai and China. And you can see in some of these images here, this is actually flooding from seawater. So the water, the sea has come inland and flooded many of the residential areas. And in this image at the bottom, you can see an intense precipitation event. Much of the city centre here is temporarily shut down because of the impending typhoon. So again, in this particular location, it's, the rising sea level is a problem, but it's this other combination of unique factors as well that actually makes the situation very vulnerable to future climate change. And in the future, it is predicted, not necessarily that we're going to see an increasing number of intense storm events, but that the magnitude of these storm events will possibly become more significant. So, there's huge areas of the world's population that are potentially threatened by the increased magnitude of storm events in coastal regions around the world. And then the last example, we can talk about coastal hazards on sort of different timescales. So some of the hazards I've just talked about are fairly short-term, instantaneous events. So for example, a typhoon will cause a lot of damage in the coastal region in a relatively short period of time. But there are other parts of the world where perhaps slightly slower processes are causing similar damage, but over a longer period of time. And one example of these is the west coast in Africa, so the coastline of countries of Togo, Benin and Ghana in particular. In these parts of the world, much of the coastline here is retreating by about 1.8 metres per year. So it's one of the most rapidly eroding coastlines that we have around the world. And in these locations, in these particular countries, the population is highly dependent on the coast for health, for food and for economic activity. And the coastline is retreating at a rate of about 1.8 metres per year. Flooding is increasing because of increasing storminess due to climate change, and people's livelihoods are effectively being taken away because the coastline on which their livelihoods are based is slowly being cut back by the sea. And it's parts of the world like this where we have, often quite marginalised populations that are the most vulnerable and most at risk to coastal hazards and rising sea levels. So again, after this talk today, there's a link here to a little video at the bottom of the slide here. This is a video by the World Bank talking about coastal erosion and storminess in West Africa and how it's affected some of the local populations over time, and more importantly, what the plans are to try to mitigate those hazards and try to protect the coastline for the future. So hopefully that's given you a little taste of different coastal environments around the world and some of the different hazards that these environments are facing. So if we think about any one location around the world, there's a combination of different factors that make that particular location vulnerable. And if we then superimpose the risk from rising sea levels on top of that, we have, potentially a very big problem in terms of managing the coastline for the future. So successful coastal management requires an understanding of the concepts of magnitude and frequency. So magnitude is the intensity of events. Are we talking about instantaneous high magnitude events like tsunamis, typhoons, etc.? Or are we talking about sort of less intense but perhaps longer term processes like coastal erosion? Doesn't have quite the same intensity or magnitude as something like a typhoon or tsunami does, but over a longer time span can do similar damage to a coastline. So the frequency is in terms of how often these events happen. So to manage the coastline, we have to have an understanding of how the magnitude of these events are going to change in the future, the frequency of these events are going to change, and importantly, a knowledge of what future sea level change is going to do. And this is where my research fits into the sort of coastal management and coastal hazard debate. So why research sea level change? So sea level change is a really important driving mechanism for coastal change. As I've mentioned already, sea level change actually operates on a number of different time spans. So multiple processes affect the level of the sea, some of them very short-term processes, some medium-term processes, and some longer-term processes. For example, the shift from glacial to interglacial cycles. I would argue that sea level change is probably the most important driving mechanism of coastal change, because if you change the level of the sea, you impact on all other coastal processes. So if you change the level of the water, you impact, for example, coastal erosion, you impact where and how sediment is transported, and you impact where sediment is deposited. So by changing the level of the sea, this has knock-on implications for all other coastal processes. In addition, if you change the level of the sea, it also has knock-on implications for all other coastal hazards. So, for example, things like saline intrusion that we've talked about already, the impacts of storms, tsunamis, all of these sort of high magnitude but lower frequency events, if they happen when sea levels are rising, the impacts are even more significant. So I would argue that sea level change is probably the most important driving mechanism for coastal change, and that we really have to understand what sea levels are doing presently, what they're going to be doing in the future, in order to be able to successfully manage the coastline. So if we're thinking about predicting future sea level change, then if we want to manage the coastline successfully, then we need to think about predicting future sea level change. This particular graph on this slide is taken from the IPCC 5th assessment report. The 6th assessment report is currently being put together. But this is probably the most recent prediction that we have for global sea levels in terms of what they're going to do through to the year 2100. So on this graph, you've got this part of the graph here. These are the sea level predictions into the future. So this is predicting what sea levels globally are going to do between now and the year 2100. You'll notice there are two lines here, two sets of predictions. So sea level is obviously very closely related to climate change, one of the major impacts of climate change. And these two different predictions are based on different temperature change scenarios. What you'll also hopefully notice is that each of these predictions is associated with quite a large error bar, if you like, so an area of uncertainty. And that's because there's lots of uncertainties associated with predicting future sea level change. So, for example, we're not 100% sure exactly what the temperature change will be. Temperature and sea level are very closely related. So some of these error bars are a reflection of that uncertainty. So these are the predictions through to the year 2100. Now, in order to get to this point, it takes quite a little bit of modelling and takes quite a long time frame of scientific data. So our ultimate aim of all of us working in the sea level research community is to try to reduce the uncertainty associated with these predictions. So it would be better if we could say for sure exactly how much sea level will rise by the year 2100, by the year 2050, etc. So in order to be of value to coastal planners, people charged with managing different parts of the coastline, it would be much better to have a clear value of how much sea level is going to rise by. That's quite difficult to do because the nature of science is that much of science is uncertain. And until we can resolve some of the debates around future sea level change, it's difficult to reduce these error bars. But the ultimate aim of all of us working in the sea level community is to try to improve predictions for future sea level change so that they can be really applicable to coastal planners, coastal managers, and also to politicians who are making policy around how to utilise different parts of the coastal zone. So in order to achieve this, we do have some instrumental data to help us. So we have data from tide gauges and satellites. So this is instrumental measured data on sea level change. Now, tide gauges have been in operation around the world. The longest ones have been measuring sea level for about 200 years. So we have probably about 10 records from different locations around the world that have been measuring sea level change for about 200 years. The vast majority of tide gauge records are about 40, 50, 60 years worth of data. And this data is actually freely available. So this is open access scientific data. You can go to a website called the Permanent Service for Mean Sea Level, and you can look at tide gauge data from different tide gauges around the world. The other type of instrumental data that we have is data from satellites. So for about the last 15 years or so, we have had some satellites that are flying around across the, above the Earth's atmosphere, and they are measuring changes in the level of the sea based on things like gravitational changes, but also using, for example, infrared technology. So these satellites will tell us about, changes to sea level, and we can use that data alongside the tide gauge record to have quite a good understanding of what sea levels have been doing over the last 100, 150 years or so in total. However, this is where the problems begin, because if we really want to improve our predictions for future sea level change, we need to have a really good understanding of all of the processes driving sea level change. And some of these processes, as many of you will know, operate on much longer time spans. So things, processes associated with the shift from glacial to interglacial cycles, isostatic processes, these kind of processes operate on thousands or tens of thousands of years. So if we only have, at best, 200 years worth of instrumental data, this is not enough data to help us really understand the longer term processes driving sea level change. So this is where our problem is. We've got some instrumental data, but the instrumental data does not extend back far enough for us to have a good understanding of processes driving sea level change. So this is where my research fits into the equation. And this is where we have to rely on what we call paleo or proxy data. So we have to go back into the geological record and actually reconstruct past sea level over different time spans. And in my case, I work on about a 10,000 year time span. So we go back to the geological record, we try to understand and reconstruct what sea levels have been doing over much longer time spans, and that provides us with longer term information about the different processes driving sea level change. And then we can put our understanding of from paleo and proxy data, we can tie that together with our understanding of what's happening with the instrumental data, and we can use that information to better improve our predictions for future sea level change. So that's how my research on salt marshes, reconstructing sea level from salt marshes, fits into sort of the broader picture. So just going to give you a little bit of an insight now into my work in salt marsh environments. So I go out into different salt marshes around the world and I get very muddy. I take sediment cores. So if you imagine the surface of the salt marsh is the present day, that's what's happening in the present day environment. If you dig down through the surface of the salt marsh, the further down you go, the further back in time you go. And salt marshes are depositional environments. So as they evolve and as they grow through time, they actually preserve a record of environmental change within their sediments. So by looking at the sedimentary history of salt marshes, you can actually learn a lot about how that environment has changed through different periods of time. So here are some photos of us from a few years ago now. I'm looking quite a bit younger in these photos. Here are some photos of us in salt marshes. It's actually in Denmark. So we're using a piece of kit called a corer. And what we're doing here is we're coring down into the salt marsh and we're bringing up sediment cores that look a bit like this. Bringing up sediment cores, and then we're doing different types of analyses on these sediment cores to help us understand how that environment has changed through time. So typically, depending on location, I think that the deepest we've ever gone with one of these pieces of coring kit is about 14 meters. Each time you bring up a meter worth of sediment. So it can be quite hard work. It can be quite tough, as you can see in this photo here. But you don't have to be an expert on sea level change to know that even by looking at this sediment core here, you can tell that there's something changing in the environment. And you know this because the colour of the sediment is changing. So here we've got quite a grey clay sediment. As we move to the right in this image, you can see that the colour of the sediment changes, and it also looks like the texture of the sediment changes quite a lot. So immediately we can tell that something has changed in that environment because of the different types of sediment that we see. So I like to refer to my coring kit as my little time machine. So by taking sediment cores, we're essentially going back in time and we're digging down into these archives of environmental change to understand what's happened to this environment in the past. So once we've taken our sediment core, some of the cores that we will look at actually in the field, so we might, for example, log the different sediments in the field. We might do a description of the different sediment types whilst we're in the field, but then we will bring some of the sediment cores back to the lab to do further analysis on. So again, on the left of this slide here, this is an example of one of my cores from the study site I did my PhD in Western Denmark. This is from the Hobugt embayment. And again, you don't need to be an expert on sea level change or salt marshes to know that there is something interesting going on here in this salt marsh environment. So down at the bottom of the core here, this is the oldest part of the salt marsh. And as we move up through the core, we're coming up to the present. And the present is the present day salt marsh at the top of the core here. So even by looking at that image of that sediment core, you can tell that there's something really interesting going on in terms of the environment, because the sediment is changing quite significantly, actually. So, we go from a peaty clay into a clay to this organic rich layer. We've actually got quite a distinct sand layer in here before we go back up into sort of a more peaty organic layer in the top here. So some other types of analysis that we might do on these cores in the lab, we'll do different types of sedimentology. So we might look at things like grain size to help us understand where the sediment has come from and the nature of the deposition processes. We might do some geochemistry. So for example, we might look at heavy metals in the core to see where the sediments might be originating from. We look at something called microfossils in the core. So I work in particular with diatoms, which I'll say more about in a minute. So diatoms are a type of algae, foraminifera are a type of fauna, and we often find things like diatoms, foraminifera and pollen preserved in sediment cores. So we need to prepare the samples, prepare them in a laboratory and look at them under a microscope. And these different flora and fauna again, can give us really important information about changing environmental conditions. Finally, we would obtain some chronological control or dating for the core. And this is really important because without any kind of time constraints on this sediment core, it's really difficult to put a time frame on the changes that we're witnessing. So typically we might do something like radiocarbon dating, types of isotope dating, so lead-210, cesium-137, etc. Essentially, these are all different techniques to try to establish the age of different parts of the sediment core. So again, in this particular example on the left here, the base of this core is around about 2,500 years old. Different sediment cores will differ in their sedimentation rates and will be different ages. So it's really important to obtain that chronological control. Interestingly, this sand layer here, we've actually dated this to be fairly recent, and this is associated with the Little Ice Age, so around about the 1800s. So we take our sediment cores in the field, we bring some of them back to the lab, we do all kinds of analysis on them. So this is an example of me sampling my core here. So I've sampled this core at 1 centimetre intervals, and these things here, this is actually folded up cling film to try to preserve the integrity of the sediment core. So if you're sampling a core and you're taking out every other centimetre for lab analysis, very quickly your core is going to fall apart if you don't do something about it. So we pad out our cores with little bits of cling film to try to maintain the integrity of the core for future types of lab analysis. So I mentioned that my work focuses on using diatoms. So there's some examples of some diatoms in the images on the left of this slide. So this one here this is one of my favourite diatoms here. Quite pretty. So diatoms are a type of algae. They tend to be very well preserved in sediments. Diatoms can survive anywhere where there is any kind of moisture. So they live in moist environments. When they die, the shells that you can see here, the sort of shells are preserved within sediments. So this shell here is formed of silica. And when the diatom itself dies, this is what we see preserved in the salt marsh sediments. So they tend to be relatively well preserved, and importantly, we can identify them to species level. So this is important because different diatom species like to live in different environmental conditions. So it's really important that we know what species we're looking at in order to better understand the environmental conditions at that point in time. So having taken our samples from our sediment cores, we prep them in a laboratory. There's a few stages of different types of using chemicals, effectively cleaning the samples before we can put them on a slide, have a look under the microscope and hopefully see lots of diatoms. So hopefully we might see something that looks a bit like this. So diatoms are really good indicators of environmental change because they respond to changing environmental conditions. So for example, diatoms can respond to changes in temperature. They respond to different acidity conditions, so changes in pH. And for the purposes of sea level reconstruction, diatoms respond to changing salinity levels as well. So as the water level is changing, the saltiness, salinity of that particular environment is changing, and hence different species like to live in different levels of salinity. So when we look down the microscope, we can see different species and we can immediately say something about their environment. So if we find species that tend to live in very saline conditions, we can say, well, you know, this represents a tidal flat environment. We might, in contrast, find species that like to live in more freshwater conditions. So that will tell us that at that particular point in time, that environment would have been more of a freshwater marsh. And essentially, this is the principle on which we reconstruct sea level change. So there's a few stages in between the diatoms and getting to this point, but it's essentially some complex statistical analysis. But we rely on understanding the modern salt marsh environment. So where do these diatoms live in the modern salt marsh environment? We look at our diatom species down through the sediment core, and then we can say something about how that environment has changed through time. So we do that on a statistical basis. I'm not going to go into that today, but eventually we get to the point where we can reconstruct relative sea level for that particular sediment core in this location. So the graph we have in front of us here, this is reconstructed relative sea level change in the Hobucht embayment over a period of about 9,000 years. So it looks quite a simple graph. Don't worry too much about the detail. This graph has actually taken about 2.5 years of lab analysis and statistical work to get to this point. So even though this looks like a fairly simple graph, in terms of the field, the lab work and the analysis that goes on to get to this point is quite a lot of work. So once we've got to this point, we can start to look at things in a bit more detail. So we can look at different rates of change, see how sea level has varied over this time period. So we can do interesting things like this and different types of analysis. Once we've reconstructed our sea level, once we've looked at things like different rates of change, we can also start to think about the processes that are driving these particular trends. And that's really important. So it's one thing to reconstruct sea level change, that's great, but it's even more important to try to understand the processes driving that change, because it's an understanding of those longer term processes that go alongside the instrumental data that help improve our predictions for the future. And in this case, in Western Denmark, the key process that's driving this rising trend here is actually because the location is isostatically subsiding. So this particular study site, because of its location in terms of the last glacial maximum, it's actually isostatically subsiding, so it's sinking, and that's driving this overall rising trend in relative sea level. And that's an important finding because information on those longer term processes is really important for helping us to improve our predictions for future sea level change. So back to the graph on predicting future sea level change that I talked through quite a bit in quite some detail a little bit earlier. Ultimate aim is to try to improve our predictions for the future. So we're trying to reduce these levels of uncertainty and try to improve the predictions for the future. We have some instrumental data to help us do this, but really we have to go back to the geological record to reconstruct sea level on a much longer time span to understand the longer term processes driving relative sea level change. So by extending our sea level records into the geological past, this is helping us to understand the processes operating on thousands of years or tens of thousands of years cycle. And that information is going alongside the instrumental data and helping to improve the predictions for the future. So I guess in terms of where we are with sea level research now, is thinking about the predictability or the applicability, of these global predictions for local and regional scale. So if you are a coastal planner, coastal manager, someone charged with managing a particular section of coastline, and your job is to try to protect that coastline or develop plans to protect that coastline through to the year 2100. This graph of global sea level change is not really much use to you, because actually this is nothing more than a global average. So the 5th IPCC report was actually the first IPCC report to discuss the concept of what we call regional relative sea level change. So there's a lot of complexity in the processes driving sea level change, and actually different local and regional areas will experience these processes to differing degrees. So if there's one thing I want you to take away from this talk today, there is actually no such thing as global sea level. When we talk about global sea level rise, when you see figures about global sea level rise, these are actually nothing more than a global average. What we need to be talking about is sea level change on a local and regional basis. So the IPCC 5th assessment report was the first of the assessment reports to come out and talk about regional variability in sea level change. And there is increasing recognition now that going forward, we need to be looking at producing regional sea level rise scenarios as opposed to global averages, because global averages aren't particularly helpful in terms of coastal hazard mitigation and management. So that's kind of where we're at to in terms of sort of sea level research presently. So just a few concluding remarks to finish off. So there is a fundamental need for us to improve our understanding of past sea level change. So there are still long-term processes affecting sea level change that we need to have a better understanding of. And to do that, the instrumental data that we have from tide gauges and satellites is not enough. So we have to go back to the geological record, continue to reconstruct sea level from different locations around the world, and better understand the longer-term processes driving sea level change. Importantly, what are the driving mechanisms behind the changes that we reconstruct? So it's one thing to reconstruct sea level, but it's really important to understand the processes that are driving the change. Future sea level predictions can and must be improved. And as I said, in the last sort of 6 or 7 years, we've seen a real shift from this idea of global sea level to regional sea level rise scenarios. And that's really important because that is those kind of regional scenarios are applicable for coastal planners and coastal managers. Future sea level prediction involves the integration of key players. So it's not just scientists, but we need to work with policymakers, we need to work with modelers to really enhance these predictions for future sea level change and ultimately protect the vulnerable populations around the world and many of the coastal cities that I talked about in the beginning of this talk. And finally, our ultimate aim is to provide sea level predictions that are of real practical value. So as a coastal planner, you need to have something that's of real value to help you manage and mitigate against future climate change and sea level rise. So you need to understand what's going on a local and regional basis in terms of future sea level change. So just a couple of, a few photos of me in my fieldwork in different salt marshes around the world. So I've been really lucky in my sea level change research. I've been able to travel to a number of different locations around the world. Gets a little bit muddy at times digging holes in salt marshes, but it's a highly relevant topic, and it's provided me with a real opportunity to see different locations around the world and to work with colleagues in different institutions around the world as well. So thank you very much for listening, and I'm happy to take any questions.
Thank you, Katie. That was great, and hopefully it's given people who are interested in studying geography at university a little bit of a sort of insight into what that might include as well, because I know a lot of this with sediment cores and ice cores is another big one as well, is often not really touched on at GCSE and A-level, but I know from when I studied geography at university it comes in a lot more there. If there are any questions, please leave them on the side in the chat. But for anyone watching later, you will keep an eye on the questions as well. And Katie's email is on the presentation slide. So if you've got any follow-up questions, please do get in touch. I don't think we've got any questions coming in, so I think we'll wrap it up there. But please do keep an eye on the GEO website. We're adding more lectures and more content is being added constantly. So do make sure you sign up and have an explore. Thank you to Katie for joining me today. That was really great, and I hope everyone has a nice evening.